Okay, so this is lesson 6, interpreting graphs of linear relations. So in the last lessons, we defined what a linear relation was. We looked at mostly tables, and we talked about the relationship by the rate of change, which measures how the y values change compared to the x value. So we're just going to look at more examples here today and define a few more things, and specifically look at graphs. Okay. So when a linear relation is shown on a graph, remember that the points are going to align in a straight line. Here's an example, and we have time on our x-axis, that's the independent variable, and volume of water, it looks like, on the y-axis. Okay, so the intercepts of the graph are where the line or the relationship intercepts, that means like hits the x or the y axis. So let's talk about the one that hits the x-axis first. Okay, so not all graphs have intercepts, but usually they're significant if they are attached to a word problem. Okay, so let's look at this here. We're emptying a water tank. This point here that I'm labeling is called the x-intercept, or the horizontal intercept. Horizontal because the x-axis is horizontal. It's where the graph intercepts with the x-axis. So we can fill in this blank. The horizontal intercept, I'm going to use yellow to match the graph, is also called the x-intercept, and it's where the graph intercepts with the x-axis. Okay, so on this graph, it would be 60 minutes. Now, typically, like I said, if there's context to the graph, it might have a significant, there might be some significance to that point. In this example, this is where the volume of water would be 0. So this is where the water tank would be empty. Okay. On the other axis, the y-axis, we call that the vertical intercept, or the y-intercept. It's a shorter way to say it. It's because it's where the graph intersects with the y-axis. So you can use the terms y-intercept and vertical intercept interchangeably. This is the starting point in this graph. So in this graph, it would be 6,000 liters of water. That's the amount of water in the tank at time 0. You can say the initial volume. Initial means starting. The starting volume of water in the tank. Okay, that's our example there. Okay, so we're going to practice with some more graphs. Okay, let's look at this next graph here. Always good to just analyze a graph and see what it's doing or what it's about. So it looks like it's the amount of gas in a scooter. That's the title. We've got distance as our independent variable here. We've got volume of gas in the scooter in liters here along the y-axis. First, they're asking us here, what is the horizontal intercept? That's where the graph intercepts with that x-axis at the bottom of the graph. So here we see that's happening at 200 kilometers. Important that we include units if that's relevant. And it says, write a sentence to describe what it represents. So 200 kilometers is when the scooter runs out of gas. You can see there's no gas in the scooter at that point. So the scooter runs out of gas after traveling 200 kilometers. You don't have to say it exactly like that, but something like that. Okay, vertical intercept, that's where your graph hits the y-axis. So here we see that's happening right at this point. I'll say y-int for short, for intercept. So that's happening at 8 liters. And at that point, the distance is 0. So when the scooter hasn't traveled at all, and if you look in the question here, it says we started with a full tank. So a full tank has 8 liters of gas before you started traveling on the journey. Rate of change. Okay, so rate of change on a graph. This is where, so we're going to use the same formula as yesterday. Yes, or not yesterday, but the previous lesson. But here we're looking at a graph instead of a table. So rate of change, remember, is the change in the y values divided by the change in the x values. So the y values are shown in blue there. You can pick any 2 points on the graph to do this. I'm going to pick these 2 points right here, just in the middle of the graph, this one and this one. But you could pick any 2 and you'll get the same answer. That's the cool thing about linear relations, because the changes are consistent. So let's go from here down to here and see how much the blue changed by compared to the yellow numbers. So at this point here, we're at 50 kilometers. I'm just going to label the points. And there was 6 liters of gas in the tank. And then we went down to we went to 100 kilometers, and there was only 4 liters of gas in the tank. Again, you can do this with any 2 points. I'm just coloring to keep the colors consistent. Okay, so that means my distance went up by 50 kilometers. From 50 to 100 is a positive change of 50 kilometers. But my y values went down. My gas started at 6 liters, but it went down to 4 liters. So it's a decrease of 2 liters of gas. So these are the numbers that I want to put in my formula for the rate of change. The y values are decreasing by 2 liters every time the x values increase by 50 kilometers. You don't need to put that plus sign. It's redundant, but put it there anyways. Okay, and then remember, this is just a division. You can just simply divide, and you would get negative, because we have a negative number there, 0.04 liters per kilometer. So that means every time you travel a kilometer, the gas goes down by 0.04 liters. So let's write that in a sentence. The volume of gas decreases by 0.04 liters per kilometer traveled. Okay. All right, let's move on. What are the domain and range? Okay, this is good practice and review. For the x value, we can write it in 2 different ways. These are connected in a line, so I don't want to just list the points. We need to include every single point along that line. So looking at those x values first, the smallest x value in my domain is 0, and then the largest is 200. So you can write it like this, or you can write 0 less than equal to x is less than equal to 200. Both of those are the same thing. For the range, the smallest y value, remember you're going bottom to top for range. So the smallest y value is 0. The largest volume of gas is 8. So you can write it like that. Or you can write 0 less than equal to y is less than equal to 8. You are actually, I should be consistent here. Really the x, it's not x here, it's d for distance. I can see the x-axis has been labeled with a d, and also v for volume instead of the y value. So we should be consistent there. Okay, good. Range, so there we go. All right, let's do another one. Again, you can pause the video here to try this one on your own maybe. So it says, what are the intercepts? So this graph is showing time along the x-axis and then distance. It says the distance a person is from a wall as they walk away from it. Okay. So there isn't any place on this graph where it intersects with the x-axis. So for the x-intercept, there's none. And not every graph has intercepts, so that's totally fine. There is a y-intercept though. That's right here at the start of the graph. That's 6 meters. So this graph only has a y-intercept. Okay, rate of change. Change in the y values over change in the x values. So let's pick any 2 points. Remember, you can pick any 2 points on the graph to do this. I'm just going to pick these 2 points right here. So this point here, I'm just going to write the coordinates 4 and then 7. 4 for the time, 7 for the distance. And then for this point here, I've got 8 for the time and 8 for the distance. The y value is 8, the x value is time. So the pattern is the x value, so the y value went up by only 1. It increased from 7 to 8, whereas the x value increased by 4 seconds. So the change in the x value was 4, and the change in the y value was 1. So let's put that into our equation. So the distance, every time you go from point to point, the y values are going up by 1 meter. I'm using the units, that's important. And the x values are going up by 4 seconds from point to point. You can just divide this, so it's 0.25 meters per second. So on a distance time graph, meters per second, that the rate of change is describing how fast the distance is increasing. So it's the speed. So we can say the person speed is 0.25, so he walks 0.25 meters every second. Okay. One more here. We have a third example. So this looks like it's a cost of publishing yearbook. I have number of yearbooks ordered here, and then the total cost along the y-axis. Okay, so vertical intercept, that's occurring right here, y-intercept. And it's halfway between 0 and 1,000, so that would be at 500. And the units here are dollars, so it'd be $500. So it looks like if I order no yearbooks at all, that's my starting cost. So we sometimes call that the fixed cost in when we're talking about cost of purchasing something. So if you have to pay something up front without purchasing any items, then that would be a fixed cost. So it's like the cost. So it, actually, sorry, I'm going to start it costs $500 initially before any yearbooks are purchased. Or I'll say ordered, because that's what it says on the graph. Okay, rate of change, again, pause the video here if you want to try it on your own. It's a change in y over the change in x. So how are the blue values going up compared to the x values? So again, you can pick any 2 points. I'm going to pick these 2 points here, this one and this one. And it looks like the cost from this point to this point goes from $1,500 up to $2,000. So it goes up by 500, and then the number of yearbooks went up by 25 books. So we've got an increase in $500 for 25 more books ordered. If you divide those values, you get 500 divided by 25, $20. That means every time you buy a book, it's going to cost you $20 extra. Okay, so the y values were going up by $500. The x values from point to point are going up by 25 books. Okay, so now I'll fill in the blanks. There's an initial cost of $500. And the cost increases by $20 every time you buy a new book. So use the pattern to find out how much it would cost to order 80 yearbooks. Okay, so 80 yearbooks we would start with the $500 fixed cost, and then it costs $20 for every book, so times 80 books. And so that would be, if you add that up, it's $2,100. Okay. And now here it says determine n if C of n equals 300. So this is another practice with function notation. So n here represents the number of books. We're trying to find that, and we're given a cost of 300. So we can, or sorry, 3,000. Let's just go to our graph and see. So here's 3,000. I'm going to go over and see what n value that matches up with. It's 125. So we can write it like this. C of 125 equals 3,000. So what that means is when 125 books are purchased or ordered, the cost is $3,000. All right.